Hi, I'm Niels, and I'll explain why Timecop's work is harder than you think. This is joint work with Caroline Rees and Matthias Weller, and it's mostly about cops and robbers. Cops and robbers games are a very famous family of Persian evasion games played on graphs, where we have a team of cops and a team of robbers, all occupying vertices of the graph. And there are many variations of these games with different rules on how the cops may move and on how the robbers may move, and under which condition a robber is caught. So let's stay with a very simple version. In this version, we have a single robber and a full information game. So all cops know where the robber is and vice versa. And initially, the cops occupy vertices of the graph, and afterwards, the robber occupies a vertex. And now we alternate between cops' turns and robbers' turns. And in a cop's turn, each of the cops can decide to either stay on his current vertex or move to an adjacent one. And in a robber's turn, he can also decide to either stay on his current vertex or move to an adjacent one. And now again, we have a cop's turn, and so on. And the robber is caught if he's on the same vertex as one of the cops. So if he would move in his turn to one of its adjacent vertices, he'll be caught by one of the cops. So it's not an option for him, but anyways, in the next cop's turn, he'll be caught. And these games are very well analyzed on static graphs. So Erlebach and Spooner introduced a new version of these games played on a special class of temporal graphs. But to understand the game version on these graphs, we first have to understand the graph model. The Cops and Robbers games is played on so-called edge-periodic temporal graphs, which consist of an underlying graph G and an edge labeling, where each of the edges is assigned with a finite binary sequence. And we say that an edge exists in a time step t, if and only if the corresponding sequence is equal to 1 at position t. And if t is larger than the length of the sequence, we use the wraparound, so the modular operation, to, well, never run out of the bounds. So the edge between b and c will exist in every time step, and the edge between a and b, for example, will alternate between existing and non-existing. So at time step 0, all indices are at the beginning of the sequences, and we can see that only the edge between A and C is missing. At time step 1, we are missing two edges, AB and CE, and so on. And since we always use the modular operation, we can see that at time step 6, the indices are back at the beginning for each of the sequences, so this graph is equal to G of 0. And this comes from the fact that 6 is the least common multiple of 3, 2, and 1, so the lengths of the input sequences, which is always the case. So we can see that g of t is equal to g of t plus LCM for all time steps t, where LCM is the least common multiple of the lengths of all input sequences. So not only the edge sequences are periodic, but also the sequence of graphs is periodic. Let's move on to the actual Cops and Robbers game played on these edge periodic temporal graphs. This new version was introduced by Erlebach and Spooner, and we have a single cop who tries to catch a single robber on such an edge periodic temporal graph. Initially, the cop chooses a vertex to occupy, and afterwards, the robber chooses a vertex to occupy. And now we start at time step 0, and the cop can decide to either stay on his current vertex or move to an adjacent vertex in the graph g of 0. So let's say he moves to B, and afterwards, in the same time step 0, the robber can decide to either stay on his current vertex or move to an adjacent one. And after the robber performed his move, we increase the time step by 1, so now we're looking at the graph g of 1, and the cop now can decide to either stay on B or move to C. And in the robber's turn, well, the robber is currently on an isolated vertex, so he cannot move away. He has to stay there. So now again, we increase the time step by 1. We look at the graph G of 2, and here the cop can move from C to E and catch the robber and win the game. So in this graph, the cop had a winning strategy, and Erlebach and Spooner showed that we can decide in O of LCM times n to the 3 time which of the players has a winning strategy on a given graph. and compute a winning strategy in the same running time. And note that LCM again is the least common multiple of the length of all input sequences, which might be exponentially large in comparison to the input itself. So this algorithm is not necessarily a polynomial time algorithm. Erlenbach and Spooner wanted to know if this algorithm can be improved to a polynomial time algorithm, or if this problem is actually NP hard. In the case of static graphs, we can check in polynomial time if a single cop can catch a single robber. But here on edge periodic temporal graphs, we will show in our paper that it is actually NP hard. So to show this NP hardness, we looked at an intermediate problem first, where we wanted to know if a given edge periodic temporal graph is edgeless at any time step. And if we look at such an edge periodic temporal graph, well, for this question, if he is edgeless at any time step, we do not need the structure of the graph itself, but only the edge sequences. Formally, we can call this problem periodic full character alignment, where we are given a set of finite binary sequences, and we want to know if all of them align at 0 at some index I. Here's an example with 3 sequences, and if we repeat them infinitely many times, we can check that all of them align at 0 at position 6 and also at position 14. And so this would be yes instance of the PFA problem. So it turns out that the NP hardness for this problem is actually not under this interpretation, but under a different interpretation of the input. So if we interpret one of the sequences as a deterministic finite automaton of a unary alphabet, so just a directed cycle, where we start to count at the initial state and say that the J state is accepting if and only if the corresponding sequence is equal to 0 at position J. Then we obtain this automaton, and one can easily check that this automaton accepts a word of length t if and only if the corresponding sequence is equal to 0 at position t. And if we do this for all the sequences, we obtain a set of automatons. So instead of asking if all of these sequences align at a 0 at some index, it would be equivalent to ask if all of these automatons accept a common word. And this problem is known to be NP-complete under the name of teleintersection. So our NP hardness result is not a new result, but the reduction we show gives new parameterized insight in both problems. Namely, we showed that both problems are W1 hard when parameterized by the size of X. So there is little hope for FPT algorithms when parameterized by X. That is, there's presumably no algorithm whose exponential growth only depends on the size of X. Let's take a look at the reduction. We reduce from the multicolored clique problem, where we want to know if a k-peptide graph contains a clique of size k. In this case, for k equals 3, this is a yes instance. We have a clique of size 3 in this graph. And we assume that the size of each of the color classes is a prime number and no two color classes have the same size. We can simply add isolated vertices to the instance to obtain this property. Now the reduction works as follows. For each pair of distinct color classes, we compute a sequence of lengths equal to the product of these two color classes, so in this case 6. And since the sizes of the color classes are distinct prime numbers, we know that each position in this sequence corresponds to a unique pair of vertices of these color classes. And we write a 0 if and only if the corresponding pair of vertices is adjacent. So this first pair of vertices is adjacent, so 0, 0, 0, 1, since these two vertices are not adjacent, another 1, and a 0. And this sequence now represents the edges between these two color classes. And we do this for all different pairs of color classes. So we obtain k choose too many of such sequences. So in this case, only 3. And after repeating them, we can now see that at position I equals to 11, all of these sequences align at a 0. So in this case, we have a yes instance of P of A, and the corresponding vertices of the graph form a clique. That is, 11 modulo 2 is equal to 1, 11 modulo 3 is equal to 2, and 11 modulo 5 is equal to 1. So with this index, this position, we can directly obtain the vertices of the clique. So this mainly gives the idea on how the reduction works. And don't worry, our paper is not only about hardness results, we also show positive results for the teleintersection and the PFA problem. For example, we showed that both can be solved in GCD to the power of x squared times polynomial time, where GCD is the greatest common divisor of any two lengths of sequences of the input. Let's move on to the NP hardness for the periodic Copenhagen game. So we reduce from the PFA problem and let x prime be an instance of PFA. So first of all, we blow up each character of each of the sequences by 3. So from the sequence 1, 0, we obtain the sequence 1, 1, 1, 0, 0, 0, and so on. One can now easily check that x prime and x are equivalent instances of P of A, and moreover, if x is a yes instance of P of A, then there are 3 consecutive indices in which all of the sequences of x align at a 0. And now we start to construct the temporal graph. We start with 2 vertices L and R, and add for each of the sequences of x a cycle of length 4 where all 4 edges are labeled with x. And well, we do this for each of the sequences. And finally, we add another vertex M between L and R and label the edge with 1, 0, 0 and 0, 1, 0. And this is mainly the complete construction. And in the following, we'll show that if X is a yes instance of P of A, then we can have a cop winning strategy, and otherwise we can find a robber winning strategy. First of all, let's start with the winning strategy for the cop. So suppose that X is a yes instance of P of A, then there is a time step or an index T, which is divisible by 3, such that at position T, T plus 1 and T plus 2, all of the sequences of X align at a 0. So at time step T, the temporal graph contains only the edge between L and M. And the strategy for the cop is to initially choose L as a starting vertex and do not move away until the beginning of time step T. And now we have 2 cases. First of all, if the robber is on any vertex except M and R, then suppose without loss of generality that he's on UX for some sequence X. And since both edges adjacent to UX in the underlying graph are labeled equal, we know that UX is an isolated vertex until the beginning of some time step T prime larger than T, in which this edge between L and UX exists, and the robber cannot escape his vertex in any previous time step. So the cop can now just wait on vertex L until the beginning of this time step T prime and catch the robber, since the cop always moves first in every turn. So in this case, we have a cop winning strategy. So we only have to look at the cases where the robber is either on M or on R. So, well, there's only, in time step T, there's only the edge between L and M. So in time step T, the cop may move from L to M and catch the robber if the robber is currently on M. So in the following, let's assume that the robber is not on M, so he has to be on R. And since R is an isolated vertex at time step T, he cannot escape. So we increase the time step by 1. So at time step T plus 1, the edge between M and R is the only one existing. And, well, the cop moves first. So the cop moves from M to R, catches the robber, and wins the game. So, again, we have a cop winning strategy, and in all, if X is a yes instance, then the cop has a winning strategy. In the following, we suppose that X is a no instance of PFA, and we'll show that the robber has a winning strategy. So first of all, let's describe the starting positions. If the cop chooses L, then the robber should choose R, and vice versa. If the cop chooses UX for some sequence X, then the robber should choose VX, and vice versa. And if the cop chooses M, then the robber should choose R. Noted in the first 4 cases, the cop cannot catch the robber in the next turn, since these pairs of vertices have a distance of at least 2 in the underlying graph. So in the last case, if the cop is on M and the robber is on R, then we can easily check that the cop cannot catch the robber in any time step divisible by 3, since this edge between M and R does not exist in any of these time steps. So what you can show now is that if at the beginning of some time step t, which is divisible by 3, both players are on one of these pairs of positions, then the robber has a strategy to evade the cop in the time steps t, t plus 1, and t plus 2, and moreover has a strategy to end up in a position such that, depending on the cop's position, both players are again in one of these pairs of positions. So one can then easily show via induction that the robber has an infinite evasive strategy. And how can we show that this is the case, that the robber has this evasive strategy? Well, it's mostly because of the fact that we suppose that X is a no instance of PFA, so in every time step t, which is divisible by 3, there's at least one of the sequences equal to 1 at position t, t plus 1, and t plus 2. So in these 3 time steps, we always have this induced cycle of length 4, on which the robber can first of all evade the cop and end up in one of these pairs of positions at the end of time step t plus 2. And this completes the proof. So here we have a robber winning strategy. In the other case, we show the cop winning strategy. So all in all, this problem is NP hard. So if we take a closer look at the reduction, we can see that the size of the graph is in O of the size of X. So we not only obtain NP hardness, but also W1 hardness when parameterized by the size of the underlying graph. So for the periodic robber game, there's little hope to obtain an FPT algorithm for the parameter size of G. And we showed that this also applies on very restricted instances, like biclicks, where one of the partitions has size 2. We show it on instances where we have a cycle of length 4 with a very long path between 2 of the non-adjacent vertices. So on instances where we have 2 vertices of degree 3 and all remaining vertices have degree only 2. And we also show it for instances where we have a cycle of length 4, and after removing these 4 vertices, the remaining graph is a clique. Let's move on to some open questions. So, it would be interesting to know if the periodic cop and robber game is actually contained in NP, or maybe like p-space hard. Also, it would be interesting if the hardness holds if there is at most one edge in every time step. In one of our reductions, we show that the hardness holds even if there are at most 2 edges in every time step. Or it would be interesting to know if the hardness holds even if the graph is connected in every time step. In most settings, temporal graphs are assumed to be connected in every time step. This is not the case here in this periodic cop and robber game, so it would be interesting if maybe the robber has an easy way to escape if the graph is connected. Well, thanks for your attention and goodbye.